Now, good afternoon, students. Today we are going to discuss our last polycyclic hydrocarbon to a polynuclear compound, that is phenanthrene. Now, already we have discussed when we are discussing the anthracene. Phenanthrene is also going to have the fusing of three benzene rings, but the fusion of all those three benzene rings, it is at an angle. In case of anthracene, the fusion will be taken place in the linearly manner. Means all the three benzene rings are linearly fused together. But in the case of phenanthrene, the fusion of those three benzene rings at an angle. See, in this structure, we are going to see that they are fused at an angle. Now, the numbering of this phenanthrene structure. Now, we know according to IUPAC nomenclature system, we are going to give the number to this compound in which the double bond containing compounds will carry the least number of carbon atoms, the least number. So, we may start numbering either from this ring or from this ring. We can number this structure by both the ways, by starting from this ring or from this ring. But now it is an isomer with anthracene. What are the meaning of the word isomer? Isomer is nothing but same molecular formula but different structural formula. We know the compound, or we know the meaning of the word isomer. So this phenanthrene is an isomeric with anthracene, and it is an example of angular polynuclear hydrocarbon. Just now we have discussed that it is going to have the fusion of all those benzene rings at an angular position. So at an angle they are going to join with each other. It occurs in the anthracene oil fraction. So whenever we are going to derive or obtain this phenanthrenes, we are going to obtain from the anthracene oil. Whenever we are deriving the anthracene from coal tar fractions, that time only we have discussed that time whenever we are discussing the anthracene source. That time we have discussed that some of the fractional impurities of phenanthrene is also there in that coal tar fraction, as it is structurally related to some of the alkaloids. This phenanthrene structure is resembling, it is related to some of the alkaloids like morphine, which is used as an analgesic compound. So morphine, the structure, it is resembling with the structure of phenanthrene, and it is also resembling with the structure of cholesterol. So you have studied the structure of cholesterol. So whenever we are going to compare this structure with the cholesterol molecule, so it is resembling, it is looking like that of structure of cholesterol. Now, this is the first way of numbering the structure of phenanthrene. Now, what is our second way in which we can number the structure of phenanthrene? Already I have discussed that in this manner also we can number the structure of phenanthrene by giving or by starting the numbering from this benzene. Now, if I am going to compare both the structure, this structure with our previous structure, with this structure. See, these two carbon atoms either may behave 9-10 position. So this will be 9 and this will be 10. Or the second numbering criteria, this is going to have the numbering 9 and 10. Means, if we are going to start the numbering in this way or from this ring, this carbon will carry 10 number and this carbon will carry 9 number or 9 number position. If I am going to start the numbering from this ring, so that time this will be 10 and this will be 9. So this is going to have the 9 and 10 position. Now why I am focusing in these two carbon atoms? Because while we are discussing all angular polynuclear hydrocarbon, that is phenanthrene, these two positions are very reactive. In the structure, these two positions are very reactive in terms of chemical point of view or in terms of chemical reaction point of view. Now, if we are going to discuss the substitution isomer. Now already the phenanthrene is an isomer of anthracene. But if we are talking about the isomerisms of phenanthrene, so if we are going to substitute phenanthrene in case of mono substitution, so only one substitution will be done, and in the case of phenanthrene molecule, now that type substitution either at 9th position or at 10th. Now we know with respect to this structure, either 9th position is active or 10th position is active whenever we are going for mono substitution. So that time the isomers we are going to obtain is of either 1, 2, 3, 4 and 9. So we are going to change the structure in this either these mini isomers we are going to obtain. Now if we are going to substitute both the position 9 and 10, that is di substitution, so we are going to obtain a higher number of isomers, that is 25 isomers we are going to form when the phenanthrene ring is di substituted. Now how we have outlined that of anthracene, naphthalene, the determination of position of double bond. Now, in a coming slide or in the displayed slide, these are the 5 important resonating contributing structures of phenanthrene. See, these are the resonating structures. We know benzene or benzene-like compounds are going to have the pi cloud of electrons on their carbon atom, and this pi cloud of electrons on the p orbital is continuously migrating, and due to this migration and jumping of those electrons, this benzene and their derivative compounds will show a resonance. Now, in case of phenanthrene also, as it is an polynuclear hydrocarbon of benzene derivative, he is also going to show the resonance. Now, depending upon the change in the position of the double bond, they are going to show the resonance, and these are the 5 important resonating structures of the phenanthrene. All are going to have the position at an angular manner only, but the position of double bond will be varies, and they are going to show the resonance. Now, C9 and C10 bond to have more double bond character. Whenever we are comparing these structures, in that the carbon number 9 and 10 are going to show the more double bond character. That's why they are more reactive with respect to chemical point of view. Now, synthetic methods for the preparation of phenanthrene. Now, the first method for the synthesis of phenanthrene is we are going to use naphthalene as a starting material for synthesis of phenanthrene. Now, in which naphthalene is condenses with succinic anhydride. For the synthesis of phenanthrene ring, just now we have discussed the structure as it is an fusion of 3 benzene rings. Now for the synthesis of phenanthrene, we are going to use a starting material, that is naphthalene, which is an fused benzene ring of 2 benzene rings. So this naphthalene will condense with succinic anhydride in the 2 position. But this also gives phenanthrene when treated as. Now the no anthracene is formed since now whenever we are condensing naphthalene with the succinic anhydride, there is no formation of anthracene will take place. Only phenanthrene will be synthesized by fusion of naphthalene with succinic anhydride. The reason behind that why now anthracene is not formed, since link closure in only the first position of the naphthalene and not at the third position of naphthalene. So the first method for the synthesis of naphthalene phenanthrene is by using naphthalene. It is very useful for preparation of alkyl phenanthrene. So this method is used for the synthesis of phenanthrene also and for the synthesis of alkyl phenanthrene also, with the alkyl group in the known position. So after ring closure, 1-methyl phenanthrene may be obtained by the action of methyl magnesium iodide on the ketone. Now, in coming slide, we are going to discuss the synthetic method for the preparation of phenanthrene. So this is a scheme of synthesis of phenanthrene by Haworth method. By Haworth method, we are using the naphthalene as a starting material which will be fused with the succinic anhydride. This fusion is taken place at angular position in the naphthalene in the presence of aluminum chloride. Now, followed by reduction, there will be formation of a carboxylic acid. Now, this carboxylic acid with subsequent oxidation will form phenanthrone, and this phenanthrone again on oxidation or metal reduction, there is synthesis of phenanthrene molecule. Okay, so in this manner, we are going to synthesize the phenanthrene by Haworth method or Haworth synthetic methods. So they may ask this synthetic procedure for the formation of phenanthrene from naphthalene. So the first method which we have discussed is Haworth method. Now, second method for the synthesis of phenanthrene is SOR method, in which P is silent, that is SOR synthesis or SOR method. This method is carried out by heating orthonitrophenaldehyde. So in which we are going to heat the orthonitrophenaldehyde with sodium beta phenyl acetate in the presence of acetic anhydride. And this, that is heating of orthonitrophenaldehyde with sodium beta phenyl acetate, is known as Perkin reaction, followed by reducing and diazotizing the product alpha phenyl nitrosinamic acid and the treated with diazonium salt with sulfuric acid and copper powder. Phenanthrene 9-carboxylic acid is produced, and this on strong heating forms the phenanthrene. So what will be the synthetic procedure? Give a synthetic route for the formation of phenanthrene by using orthonitrophenaldehyde. So what we will do first? First we will treating or heating orthonitrophenaldehyde with sodium beta phenyl acetate. So heating of the orthonitrophenaldehyde with sodium beta phenyl acetate in the presence of acetic acid, or sorry, in the presence of acetic anhydride. So there will be a formation. So this particular reaction is known as Perkin synthesis of acid. So it will result into an formation of this intermediate product, which will be reduced further and diazotizing to form alpha phenyl orthosinamic acid. So this is an orthonitrophenol sinamic acid. So this is an orthonitrophenol sinamic acid. Now this and treating with diazonium salt. So this compound, this nitro compound will be reduced with this metal reduction. It is converted into amine functional group. As it is an primary amine, we are going to diazotize it with diazotization in the presence of sulfuric acid and copper powder. Here there will be requirement. So there is formation of phenanthrene 9-carboxylic acid. And this phenanthrene 9-carboxylic acid again in the presence of copper powder will be reduced and there will be a formation of phenanthrene. So two methods are there for the synthesis of phenanthrene: Haworth method and SOR method. Both method we are using naphthalene as a starting material. In case of SOR method, we are using orthonitrophenaldehyde as a starting material. So these two are only the synthetic methods or synthetic procedures agent for the formation of phenanthrene molecule. Now, by using an Haworth synthesis method, we already discussed there are two methods for the synthesis of phenanthrene, Haworth and Shaw. So this Haworth method is also used for the preparation of alkyl phenanthrene. That time also we have discussed it is used for the formation of alkyl phenanthrene also with an alkyl group at known position. So we know whenever we are substituting that time that position we can substitute by using an selective method, that is Haworth synthesis method. So this is an application of Haworth synthesis method. So this is a reaction for the formation of alkyl phenanthrene by using an Haworth synthesis method. So this is an intermediate product by synthesizing phenanthrene with naphthalenous starting material. This again on treatment with Grignard reagent and water. So there will be formation of an hydroxyl derivative, and this hydroxyl derivative further reduced in the selenium. There is formation of 1-methyl phenanthrene, which will be obtained by the action of methyl magnesium iodide on the ketone. So this will be synthesized, that is alkyl phenanthrene can be synthesized by using an intermediate product from the synthesis of phenanthrene by Haworth method. Also, we can synthesize two alkyl phenanthrene. This is one alkyl phenanthrene and this is two alkyl phenanthrene. So this two alkyl phenanthrene in which the same synthetic method will be used, that is Haworth method, but we can substitute the second position, that is two alkyl phenanthrene, by using a same synthetic method, that is Haworth method. So this is an Haworth method. Only we have substituted at second position of the phenanthrene with an alkyl group. So this is an application of synthesis of phenanthrene by Haworth method. Now we are moving towards the chemical reaction of phenanthrene. Now phenanthrene is oxidized in the presence of potassium dichromate and sulfuric acid as a strong oxidizing agent. Why there is requirement of strong oxidizing agent? See number of double bonds in the structure. So we require a strong oxidizing agent, that is potassium dichromate and sulfuric acid. Now this oxidizing agent will oxidize the 9th and 10th position of phenanthrene compound, and it will be converted into phenanthrene. As like that of anthracene, in case of anthracene, we are going to synthesize anthracene. Now, in case of phenanthrene, we are going to synthesize phenanthrene from a structure of phenanthrene by simpler oxidation, that is oxidation by potassium dichromate and sulfuric acid. Now, this particular reaction will require the presence of glacial acetic acid to synthesize phenanthrene. This is an orange solid having melting point 208 degrees centigrade. Now, this is an oxidation of phenanthrene. If we are moving towards the reduction of phenanthrene, now again, if oxidation is taken place at 9th and 10th position, we know the 9th and 10th position of phenanthrene nucleus is very reactive. So, particular reduction is also taken place at that position only, that is 9th and 10th. So, by using an sodium metal in the presence of ethanol, if we are going to reduce the phenanthrene, so there is formation of 9-10 dihydrophenanthrene. So, we are going to obtain 9-10 dihydrophenanthrene by reduction. So, this coming slide has summarized the overall reactions of phenanthrene. This is an heating with the help of sodium metal. Just now we have seen the reaction. that is the formation of reduction reaction, formation of 9,10-dihydrophenanthrene. If we are oxidizing phenanthrene in the presence of ozone, that is ozonolysis reaction. We know whenever we are going to use ozone, that particular reaction is known as ozonolysis. So the reaction of phenanthrene with ozone, that is ozonolysis procedure, will form biphenyl 2,2-dicarboxyaldehyde. That means we are heating the ozone with, we are heating phenanthrene with ozone. So there is a total reduction of that. Third ring will be taken place again at 9 and 10 position. So there is formation of biphenyl 2,2-dicarboxyaldehyde, dicarbaldehyde. If we are going to brominate phenanthrene, so the bromination reaction will be taken place again at 9 and 10 position. So blindly you can write the substitutions at particularly 9 and 10 position whenever there are substitutions. So simple reactions are there. So whenever we are going to brominate or halogenate the phenanthrene ring, halogenation will be taken place at 9 and 10 position. So that is formation of compound 9,10-dibromo, 9,10-dihydrophenanthrene. If we are doing a specific bromination in the presence of ferroborate, so there will be a substitution of only one bromine nucleus in the structure of phenanthrene. So there is formation of mono substitution product, that is 9-bromo, 9,10-dihydrophenanthrene. So only mono substituted product. This is the entire substituted product. Then if we are reacting the phenanthrene with hydrogen peroxide in the presence of alcohol, so there is formation of diphenic acid. So these are the chemical reactions are there with the phenanthrene nucleus. So in today's lecture we have covered what is phenanthrene, how they are numbered. So in case of today's lecture we have covered what is phenanthrene. It is an isomer of anthracene. The numbering positions of phenanthrene. At an angular position, it is fused with the 3 benzene rings. These are the resonating structures as well as position on some double bond in those all resonating structures. Then we have discussed synthetic methods for the formation of phenanthrene. 2 methods are there, Abbott method and Saul method. In case of Abbott method, we have utilized naphthalene nucleus as a starting material. For Saul method, we have used the orthonitrophenaldehyde as a starting material. So these are the applications of Abbott method for the formation of alkyl substituted derivative of phenanthrene. If the alkylation is at first position, then this will be the synthetic route. If the alkylation is at second position, now this will be the synthetic route for the formation of phenanthrene nucleus. Then we have discussed chemical reactions of phenanthrene, oxidation, reduction, and in this slide we have discussed overall all chemical reactions of phenanthrene nucleus. Now, already we have discussed that phenanthrene and anthracene are isomers of each other. Now, when we are going to do the electrophilic aromatic substitution reaction in anthracene or phenanthrene, that time we can yield a mixture and is not generally useful, because when we are going for the substitution of electrophilic aromatic substitution reaction, for example sulfonation, we are going to obtain the mixture of compounds, that is bromination. We are going to obtain the bromination product of anthracene and phenanthrene is in the percentage. But when we are going to do the specific bromination in the presence of phenanthrene ring, so that time already we have discussed this reaction. This is a mono-substituted bromination, that is at ninth position, and in the presence of carbon tetrachloride, this bromination will be taken place. It is a di-substituted bromination. 910 dibromophenanthrene and 9 bromophenanthrene we can obtain by bromination reaction of phenanthrene. So this is all about which I am going to convey with respect to the phenanthrene